India's Tejas Mark II medium-weight fighter is being designed to achieve approximately 82 to 85% indigenous content by value. The aircraft is anticipated to feature numerous indigenous systems, including a quadruplex digital fly-by-wire system, digital flight control computer, wide-area display, mission and cockpit software, unified electronic warfare suite, missile approach warning and countermeasure technologies, UTM ASA radar, and an infrared search and track system. The Tejas Mark II prototypes are to be powered by imported GE F414 engines, though the production aircraft are expected to be fitted with domestically manufactured power plants. The ejection seat will also likely be of foreign origin till Indian systems attain maturity. The Tejas Mark II program intends to give Indian organizations and industry greater control over core technologies. The program is also expected to support the development of the advanced medium combat aircraft by providing experience in integrating indigenous sensors, avionics, flight control systems, and weapon systems. Future Indian Army integrated battle groups could use a layered unmanned network to detect, track, disrupt, and destroy enemy forces before they reach Indian defensive positions. The outer zone is likely to extend up to 40 kilometers into enemy territory and could use long-endurance drones to monitor enemy assembly areas, logistics nodes, and artillery positions. A second zone could use long-range loitering munitions, precision artillery, FPV drones, and precision-guided munitions to target artillery batteries, command vehicles, air defense radars, and other critical infrastructure. The final defensive zone could use shorter-range systems against tanks, infantry fighting vehicles, and assault engineering vehicles approaching Indian defensive positions. Counter-UAV systems would operate throughout the network and would use mobile anti-drone radars, electronic warfare systems, directed energy weapons, and interceptor drones to detect and neutralize hostile systems. AI-enabled command systems could process information from sensors and drones, prioritize targets, allocate weapons, and coordinate operations. Together, these layered capabilities could give integrated battle groups a persistent, networked defensive architecture capable of disrupting enemy operations well before they reach the front line. India and the United Arab Emirates could develop regional maintenance, repair, and overhaul capabilities for Rafale aircraft. The UAE currently has 80 Rafale F4 aircraft on order, while India is planning to induct 114 aircraft in addition to the 36 in service and 26 on order. If all planned acquisitions are completed, the combined fleet of both nations could exceed 250 aircraft. While Safran Aircraft Engines is establishing an M88 engine MRO facility in Hyderabad, Dassault Aviation and Tata Advanced Systems Limited are expanding Indian production of structural components and fuselage assemblies for Rafale fighters. India is also developing domestic maintenance capability for the Rafale's MICA air-to-air missile through cooperation with MBDA. A regional support network for Rafale fighters could reduce transportation distances, maintenance turnaround times, and increase fleet availability. It would also provide Indian technicians and engineers with experience that could support the Tejas Mark II and AMCA programs. DRDO's Naval Physical and Oceanographic Laboratory has issued a request for proposal for the development and supply of viscoelastic isolation mounts. Viscoelastic isolation mounts are designed to reduce the transmission of mechanical vibrations from diesel engines, gas turbines, generators, pumps, compressors, and other machinery to the ship's structure. This leads to a reduction in underwater acoustic signature and makes it difficult for passive sonar to detect vessels. It also decreases mechanical fatigue, extends equipment service life, improves crew comfort, and supports the performance of sensitive equipment such as sonars, radars, and electronic warfare systems. The development of viscoelastic isolation mounts supports the indigenization of naval equipment and could provide critical technologies for use on upcoming surface combatants, submarines, and other defense platforms. IIT Kharagpur has received funding to develop and experimentally demonstrate a gas turbine-based rotating detonation engine propulsion system. The effort also covers experimental testing to study detonation physics, combustor design, turbine integration, and propulsion system control. Unlike conventional gas turbine engines, which use relatively slow and continuous deflagration-based combustion, a rotating detonation engine uses rotating detonation waves to release chemical energy from a fuel-air mixture. Such power plants provide higher thermal efficiency, lower fuel consumption, higher specific power, and greater propulsion efficiency. The effort could provide India with experimental knowledge for developing RDE-based propulsion systems that can be used for aerospace and other high-performance applications.